All right, guys, here we go, jumping into chapter 2. We're going to start getting some introduction to some proofs and a whole lot of geometric postulates and theorems and definitions and all those fun things. So we will be leaving out two of the sections that are a little less needed and not required. So we're going to be leaving out sections 2.2 and 2.4. But we'll be covering the rest. So it starts out with this idea of inductive reasoning and making a conjecture. So inductive reasoning, and hopefully you print these out. I always hope you guys do, because it always comes with the vocab and things like that that would be helpful. So, but inductive reasoning is when you come to a conclusion based on some kind of a pattern or past experience that you see. And so when you make those types of conclusions, the conclusion is called a conjecture. It is not something that we can prove, and it is something that could possibly be wrong, but it is the conclusion or the assumption that we would make just based on our past experience or patterns or whatever evidence that we have. So let me give you a quick example before I actually jump into the math ones. If I would ask you guys, let's just say it's somewhere in the middle of the summer, like August or July, and I said, hey, if we go to the beach on Labor Day, right, in September, Labor Day, if we go to the beach, what do you expect it to be like? You would probably say it's going to be hot, it's going to be crowded, a lot of people there, all that type of stuff. And why are you making that conclusion? Well, you would make that conclusion based on your past experiences. In the past, if you've ever been to the beach on Labor Day, it's probably been hot, it's probably been crowded, and so you would make that assumption or that conjecture about it being hot and crowded in the future. So you don't know for sure that it's going to be hot and crowded. It probably is, but you don't know that for sure. It's just a conjecture based on past patterns and experiences that you've had before. And so that's what a conjecture is. So it's not something that is fact. It's more of an assumption or an opinion. So look at a couple number examples here. So if I started looking at some number patterns like this, and I told you, let's start taking a look at number patterns with powers of 3, right? Where the base is 3. So if I said 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81. What do you think the next number in the pattern would be? You would probably guess the next number in the pattern is going to be 3 to the fifth, or 243. Now, is that what the next number has to be? Well, we don't know that for sure. There could be much more going on with this pattern than you really see with just the first couple numbers. It's probably 3 to the fifth. That'd be a really safe assumption or a really safe conjecture, but we don't know that for sure. It's still an assumption that you are making based on the pattern. So there could be something else going on with the pattern. Maybe the pattern repeats itself, right? Maybe it's 1, 3, 9, 27, 81, 1, 3, 9, 20. Maybe it repeats itself like that, and so the next number in the pattern is actually 1. But we wouldn't know that unless we saw more of the pattern. But so a good conjecture would be, a good assumption would be that would be 243. So same thing if you looked at, there's another example going on over here with these squares. So if we just said, so write a conjecture, or you could say make an assumption about the number of small squares in the next figure. So if I was going to draw a fourth figure, how many squares do you think would be in that next drawing, right? And you would say, well, let's see, there's 1 square here, there are 4 here, the next one has 9 little squares in it. So I think if you were going to make another drawing, let's see what this pattern is. This is 1 squared, 2 squared, 3 squared. So 4 squared would be a pretty good conjecture. We know 4 squared is 16. But that would be a pretty good assumption that you can make about the next pattern that I might draw. You don't know that for sure. It's not a fact. It's inductive reasoning, right? You're making a conjecture based on a pattern that you see. So let's move on to a couple that you guys can try. Remember with these, I always like when you guys maybe pause the video, try this problem on your own, and then play the video to see if you did it right. So you can always do that at any time. So if I have a number pattern here, of course we're going to focus on math patterns with things like this, but if I wanted to write a conjecture about describing this pattern or identifying the next term in this sequence, what would it be? So I do see that the signs are alternating, negative, positive, negative, positive. So I would maybe make the conjecture that the next sign of the next term is going to be negative. And if I look at these, it looks like the pattern is being multiplied times 2. Because 5 times 2 is 10, times 2 is 20, times 2 is 40, times 2 is 80. Right? And so if I was going to make a conjecture, that would probably be a really good assumption about the next number in the pattern. I don't know that for sure. It's not based on a fact. This is simply based on what I see in the pattern. Okay, and so I would make the assumption that the next number is negative 80. Let's try it with this one. What might help with this pattern is if you see 1 as 5 over 5. That might make this pattern a little easier to see. I'm even going to write that out. So instead of the first term being 1, I'm going to write that as 5 over 5, because that's still 1, right? So 5 over 5, 6 over 5, 7 over 5, 8 over 5. What do you think the next number in the pattern is? Most likely, I think we would assume that it's going to be 9 over 5. Right? And that would be a really good conjecture. That's definitely what I would expect the next term to be. Like I mentioned before, it doesn't have to be that. There could be a different pattern going on that maybe I just haven't seen yet. We don't know that for sure, but this would be a pretty safe conjecture to make, right? A good assumption to make. Something we would expect to happen. Let's take a look at this one. So what if we said write a conjecture about each value or geometric relationship? So angle 1 and angle 2 form a right angle. So what is a conjecture, or what is an assumption you could make about that information? So if angle 1 and angle 2 form a right angle. And do keep in mind there can be more than one right answer for something like this. But when I see information like 1 and 2 forming a right angle, what do we know about the measure of a right angle, right? We know it's 90 degrees. So if angle 1 and angle 2 form a right angle, then my assumption would be that angle 1 plus angle 2 equals 90 degrees, right? That would be my conjecture because that's certainly information that I could write based on what I see right there. So that would be a great conjecture. Like I said, you might come up with something else, but make sure it's at least reasonable for the information that you were given, for sure. Vertical angles. So this is something that came up in chapter 1. We know vertical angles look something like this. Let me just remind you. So if you think of an X, it's usually an X that forms vertical angles. Vertical angles are the ones that are across from each other in an X. So like that one and that one would be considered vertical angles. Well, what do we know about vertical angles? We know that vertical angles are congruent. They have the same measure. So whatever they are, I know they're the same. So my conjecture would be something like that angle ABC is congruent. Remember, that just means they have the same measure, they're the same size. So angle ABC is congruent to angle DBE. All right, that's definitely a conjecture I would make based on the information that I've seen here. And again, remember, this is all based on like previous knowledge, past experiences, or patterns that you've seen before. So if you would maybe think back to chapter 1, you would say, well, let's see, I learned in the past that vertical angles are congruent. So based on my past knowledge, I would make this conjecture right here. So let's peek at one more of those. So, and again, you can always pause this and give this one a try before I do it. But for number 5, I would say angle E and angle F are right angles. So I'm going to give you a quick drawing. So I want you to see this. So let's see, here's angle E. It's a right angle. Angle F is a right angle. So here's what they're telling us is that E and F are right angles. So what could we say about that? And there's a couple things you might have come up with for this one. First of all, if they're both right angles, you might say that angle E is 90 degrees. You could say angle F is 90 degrees. You could say angle E is congruent to angle F. That would have been a good conjecture, right? They're congruent because they're both 90-degree angles. They're both right angles, therefore they must be congruent to each other. They have the same measure. We could also say that they are supplementary. So if you think back to something else we learned in chapter 1, that we were learning that vocab word of supplementary angles. Remember, supplementary angles are two angles that add to 180 degrees. So if he's 90 and he's 90, I know they add to 180. So you could say that angle E and angle F are supplementary. That would be a good conjecture. All right, that's information we're pulling out of that given information that we have right here. So anyway, a lot of good right answers on that one. Hopefully that helps. Let me take you to one more page. We're going to talk a little bit about counterexamples. So this is a really important concept here of what's going to be coming up in this chapter is this idea of a counterexample. Counterexample is something that you would use to prove a situation to be false, right? So if you say some conjecture is false, then I need to give a counterexample to prove why it's false, right? So here's their example that they came up with. So let's just talk about theirs, and then we're going to try some of our own here. So if segment AB is congruent to segment BC, then B is the midpoint of AC. So if you take a look at the drawing over here, so does that have to be true? So if AB is congruent to BC, then B is the midpoint of AC. So remember, this is a conjecture, right? So somebody saw this information and they said, oh, AB is congruent to BC? Well, if that's true, then my conjecture is that B is the midpoint of AC. Because in their head, they might have been thinking this. Here's A, here's B, and here's C. And if AB is congruent to BC, so that means this segment is congruent to this segment, well then B has to be in the middle. And that could be true. That's certainly a possibility, but is there anything that could prove that to be a false conjecture? Does B have to be the midpoint of AC? So here's the drawing over here. This is their counterexample. They're saying, yeah, ABC doesn't have to be in a straight line. So just because this was your conjecture doesn't mean that it's necessarily true, right? Because here is a counterexample, right? What if ABC was drawn this way and not in a straight line? AB is still congruent to BC, but B is no longer the midpoint, right? Because ABC in this drawing is not a straight line. So B is no longer the midpoint if you drew it this way, right? And so just because it could be true doesn't mean that it has to be true. This is a counterexample that would prove this conjecture to be false, right? So remember, the way this always sets up is the if statement. You're going to get real familiar with if-then statements. These are a big part of this chapter. But if, so this is the given information. This is what we know to be true. So if this is true, then what would you conclude, right? And then the conclusion is this. And so the conclusion is our conjecture. This is an assumption that was made, is at the midpoint of AC, right? So, but this, again, we can prove conjectures to be false with a counterexample. So let's try some of these on our own. So determine whether each conjecture is true or false. But if you say it's false, you have to be able to prove why it's false by giving a counterexample. So if A, B, and C are collinear, means they're on the same line, then AB plus BC equals AC. So this was something that came up in chapter 1 about the segment addition idea. So it says A, B, and C are collinear. So here's the conjecture. Someone said, okay, well, if you're telling me that A, B, and C are on the same line, then my conjecture, my conclusion, is that AB plus BC equals AC. Does this have to be true in all cases, or can you think of a counterexample for where this wouldn't be true? Here's what somebody was thinking, right? If this was their conjecture, then what they were thinking was that A, B, and C look like this. So this is what came up in their head for why they said that this statement has to be true, right? And if it was drawn this way, then yeah, it's true, right? AB plus BC is equal to the whole thing, which is AC, right? That would be true if it was drawn that way. But is there another way we could draw it? So can you still draw A, B, and C on the same line, collinear, on the same line, but this statement's false? Let's see, what if it was drawn this way? C, B. So if we drew it this way, this still keeps this information intact. A, B, and C are still on the same line. So my given information is still true. They're still on the same line, but is this conclusion still true? It's not, right? Because now AB, the whole thing, plus BC is equal to AC? That wouldn't make sense, right? AC is clearly smaller than AB. And so this drawing would be a good counterexample to this conjecture. Let's look at another one here. So if angle R and angle S are supplementary, remember what supplementary means. We learned this in chapter 1. Supplementary means that these two angles add to 180 degrees. And so this is still part of the given. Angle R and T are supplementary. Then, so here comes the conjecture, right? Your conjecture follows this word then, right? Whenever you see the word if, this is the given information. This stuff is true. This is the scenario they're giving you. So they're saying, okay, if R and S are supplementary, that's true. R and T are supplementary, that's true as well. What's your conjecture? So here's the conjecture. Here's the conclusion that they made. Well, that means then that angle T and angle S are congruent. They're the same angle. Is that true? Let's see. If angle R and angle S is 180, right? If when I add them together, they're supplementary, they add to 180. Angle R and angle T equal 180. Is it true in all cases that T and S must be the same angle, that they're both congruent? Can you think of a counterexample? You cannot think of a counterexample because this statement is true in all cases. If those guys add to 180 and those guys add to 180, then these two angles must be the same angle. I'll give you numbers here to prove it. Okay, so what if angle R was 60 degrees? So I'm going to put this in for angle R. So still 60, still 60. Okay, so this is angle S and this is angle T. So 60 degrees, so whatever angle R is, what would I have to add to that in order to get 180? Right, so if angle R was 60, that would have to make angle S 120 in order for that equation to be true, right? There's no other value I could put there if R is 60. Well, if R is 60, what would angle T have to be in order to make 180? Well, angle T would also have to be 120, right? So if angle R is 60, then these guys both have to be 120. And if you keep changing the number for angle R, you'll continue to find that whatever this is, this one has to be the same. So it is true that angle T and angle S are congruent. They're both the same angle, right? And there's actually a theorem to this that we're going to be using as this chapter goes on. It's called the congruent supplements theorem. And it just means that if two angles are supplementary to the same angle, then those two angles must be congruent to each other. So that one is a true statement. So we just write true for that one. If you cannot come up with a counterexample, we just write true. Okay, two more here. If angle ABC and DEF are supplementary, so again, these two angles add to 180, then here comes the conclusion, here comes the conjecture, then those two angles form a linear pair. What do you think about that one? Is it true in all cases, or can you come up with a counterexample? Let's see. So I'm going to draw, remember what a linear pair is. A linear pair is two angles, I'm going to draw it for you, that form a line, right? It's a pair of angles that form a line. So here is angle 1, and here is angle 2. So those are two angles that form a line, right? This angle plus this angle form this line that you see right here. So that's what a linear pair is. So, and remember that lines are 180 degrees. And what does supplementary mean? Two angles that add to be 180 degrees. So can you think of a counterexample or another way to draw this to where ABC and DEF are not a linear pair, but they're still supplementary? They still add to 180. So I have to keep the given information intact. This still has to be true, but this, the conclusion, is no longer true. What if we drew it this way? So what if this was angle ABC? And let's just say it is 130 degrees. And angle DEF, so DEF is 50. So are those two angles supplementary? They are, right? They add to 180. So the given information is still true. However, are they still a linear pair? Do they form a line? Not if they're not touching, right? If they're drawn this way, they form a line because they're connected, right? They share a common side. They're adjacent, right? Those are all the vocab that we learned in chapter 1, right? These are adjacent angles that form a line that are supplementary. But these guys are not adjacent. They're not touching, right? They're still supplementary, so my given is still true, but they're no longer a linear pair because linear pairs have to be connected like those are. So this would be a great counterexample right here. Last one is that if segment DE is perpendicular, remember perpendicular lines, you remember from algebra, are just two lines that form a right angle, right? So if this is a line and this is a line, so those lines are perpendicular if they form a right angle. Okay, so they're segment DE and segment EF are perpendicular. So that's the given information. This has to be true. That's what we've been given. Here's a conclusion they made. Angle DEF is a right angle. So does this have to be true if this is true? Can you think of a different way to draw that to where this would still be true, but then this would be false? So let's take a look. So DE and EF. So certainly if I drew it this way, so here is DE, EF, so from E to F, so here is EF. So if these two segments are perpendicular to each other, then is the angle DEF, this one right here, have to be a right angle. This is one that is true. Right? There's no other way about it. By definition of perpendicular lines, if two segments are perpendicular, they must form a right angle. So in order for these two segments to be perpendicular to each other, they must form a right angle. So that has to be true. There's no other way to draw that based on definition of perpendicular segments. So anyway, that is it for the start of the chapter, and to be continued.